Today we're going to talk about design of rectangular beams. From the last series that I've done for design guidelines, if you don't know what I'm talking about, the links are in the description. Today we're going to design a simply supported beam. But before that, I've gathered many information from various sources about how to do that in a very simple way. So please bear with me, and we have to go through simple steps from ACI and, as I said, from various sources to do a quick design. So the first step that we have to do is check deflection. We want the beam to deflect, but with a minimum requirement. The ACI specifies, depends on, we'll talk about beams today, so depends on its situation. If it is simply supported, then it's L over 16. One end continuous, it's L over 18.5, L over 21, L over 8, right? We all know what's this. Just to recall quickly, simply supported is this type of beam, right? Roller and pin. If it is one end continuous, it will be here, so we're talking about here. This is called one end continuous. Both end continuous is actually this one, which is in the middle, and this is called cantilever, right? It's a quick review. How to reduce the deflection is by increasing modulus of elasticity and moment of inertia, because these two values represent the stiffness of a beam. If the beam was stiff, that means the deflection will reduce. All right, that's the first aspect. So what are these? These are the minimum thickness, which is h, the depth of the beam. So depth of the beam equal L over 16 if it is a beam and simply supported. But this is the minimum value. So I can go more than that. I can do L over 10, for example, to be in a safe side. Okay, the second thing that ACI specifies, and as I said in the various sources that I've used, is to do an economical beam. Economical beam, that means D over B is actually from 1.5 to 2. This is the ratio for normal span. And when I say normal span, it's from 20 feet to 25 feet, or 6 meters to 7.5 meters. So if I get H, right, by using these formulas here, and I subtract H from the cover, I will get D, and then by default I will get B if it is a normal span. If it is more than that, if the span of the beam is more than 8 meters, we will change D to B ratio to be 3 to 4. But guys, you have to check with the architect. And I mean by checking with the architect, because you don't want to be a very deep beam that is really visible by customers or the end users, so it will be a problem. Why we are doing this, guys, I forgot to mention, recall that we said in the triangle here, that it's triangle of design, we need the load, which is mu, right? And then we need BD square, which is unknown, or AS rho, which is also unknown. If you assume one of these, if you assume BD square, or you get it by this, what we are doing right now, then you will be able to compute AS and rho. Or the other way around, this is known. If you know AS or rho, you can compute BD square. This is the triangle of design. It's simple as that. Okay, so we talked about that. Then the third step quickly is to calculate the beam on weight. The beam on weight is it's simple. It's the unit weight of concrete multiplied by B times H. But usually for unit conversion, we'll divide this by 144. It's just a unit conversion. We'll see that in an example when we start solving. After that, we have to calculate number 4, the load, because we got the on weight, we know what are the loads. Then you calculate what's the moment. Moment would be for simply supported beam WL square over 8, for example. W is the load, ultimate load. But you have to factorize the load. Finally, or not finally, we still have more steps. Number 5, select the bar sizes. Select bar sizes. After you do the calculation, you calculated what's AS from here. You select the bar sizes. Selecting the bar sizes and doing that depends on a table that we're gonna see when we start solving. All right, I'm gonna show you a table in the next slides. Then we'll go to number 7. Number 7 actually is dependent on the bar spacing. Guys, when we do the reinforcement, we have to leave a spacing. The spacing between we have a clear spacing, which is from the end here of the bar. The clear spacing is from here to here. The ACI specifies that this should be 1 inch at least, or it's as equal as the bar diameter. Okay, this is called clear spacing. Why do we need that? Because this is to allow concrete to go between the bars. Because if we have let's assume that we have a bar here, which is a reinforcement, and a bar that is so close to it. When we pour, we have a concrete here, right? And we have a concrete here. Guess what? This area in the middle is overstressed. And what will happen? It will break. And then eventually you will have a reinforcement without any cover. This will, of course, allow the steel to be corroded, and you have a lot of problems. You guys all know about it. Now, and the cover from here to here also is specified. Sorry, when I say 1 inch, it's equivalent to 25 mm in the SI unit. Right, so when we go back again, the reinforcement, also the clear cover, or we have something called cover, is from the middle of the bar to here. We usually take it 2 to 3 inch. If we talk about SI unit, that is 50 mm to 70. Okay, from the middle of the bar, diameter. Okay, if you have a double reinforced, as shown here, we said from here to here it's 1 inch, right? But also from here to here it should be 1 inch. Okay, from 2 far ends, or 25 mm. Okay, that's fine. This is step number 7. As I said, the bar diameter, spacing of the bars, and this is and we talked about the cover, which is step number 8. Step number 9 is to calculate to make sure that phi mn, which is the nominal moment, is greater than or equal than the load. This is the capacity and this is the demand. If you did all of this, then your design is over. That's it. Okay, guys, let's go to the next slide and start designing. All right. So let's have this example. Assume you have a rectangular beam. Design a rectangular beam, sorry, for 22 feet span. This is the span, simply supported. Okay. If the dead load is 1 kilopound per foot, and not including beam weight, and the life load is 2 kilo per foot, use FC prime and Fy. I'll talk about this, why I put this table here. So starting with the first step, here, going to the first step quickly. So let's assume simply supported, that means H is equal to L over 16 is the minimum, but I'll go a bit higher, and this is the practical way. We will take L over 10. Okay, so L over 10 is what? Is 22 feet divided by 10, it's 2.2 feet. If you change it to inch, that means 26.4. Say, let's take 27 inch. Okay, now D from here, D equal to H minus the cover. Let's take the cover 2.5 inch, so 27 minus 2.5, that will give you 24.5 inch. This is D, right? Taking the ratio, second step, taking the ratio D over B. We said it should be from 1.5 till 2, isn't it? Let's take somewhere in the middle. Let's take 1.7. So D over B equal 1.7. And by that, you will get B to be 24.5 divided by 1.7 is 14.4 inch. Say 15. Say 15 inch. Guys, we get D, B, H, and the cover. We can compute the own weight. Own weight of the beam equals to B times H, 15, multiplied by H. Where is H? H, 27, yes. Divided by the unit conversion, because I want it to be in feet, multiplied by, yes, instead of inch, 150 is the unit weight of concrete. It's equal to 422 pounds per foot. Great. Okay, since it is simply supported, I have the loads, right? But I have to factorize the load. Going back from, recall from structural analysis course, the ultimate load is 1.2 times dead load plus 1.6 times live load. And this will give me a final load of 4.87. This is 8. 4.873 K per foot. So what's the moment? Moment is equals to WL square over 8, and this will give me 2294.8 kfoot. That's my load. Okay, now starting with the phi mn should equal mu. That's the demand, and the capacity at least should be equal. Equals to the equation that we took, guys, right? Which is phi times rho, which is the percentage of steel, BD square, multiplied by Fy, open the parentheses, 1 minus rho Fy divided by 1.7 Fc prime. Phi is 0.9, we know that, right? We got BD square, we have Fy, we have Fc prime, we have the load, which is this one. So doing this, the math, I computed rho to be 0.0078. That's the percentage of steel. Now from the percentage of steel, I can get AS, isn't it? So AS is what? Area of steel is rho BD. Rho BD, right? That's the equation. So it is 0.0078 multiplied by B multiplied by D. And this will give me 2.87 inch square. Now I have to choose an area of steel that's a bit higher than this, but not over exaggerated, because this will be over designed. So let's choose 2.9 or 3 from this table. So we go back, so we'll go to this table. I want to achieve 2.87 inches square. Now, if this gives me 1 inch square here, choosing 3 bars of diameter 9 will give me 3 inches square. So let's choose this. So again, sorry. So let's choose 3 bar 9, which is equal to 3 times 1 inch square, which is 3 inches square. That's AS. Okay, I have to check, is my solution correct? Is what I'm doing, is it okay what I'm doing? So let's check the rho percentage, because the rho will change, isn't it? So from here, rho is what? AS over BD, which is 3 divided by 15 times 24.5 this will give me 0.00816. Okay, let's continue in the next slide. Okay, so here, if I got row, again, I'll write it again. If I got row to be 0.00816, I have to check it. Is it bigger than row minimum and is it less than row maximum? So what's row minimum? We know that from the previous presentations, row minimum is actually 3 dependent on material property, right? So 3 radical fc prime over fy should be greater than or equal to 100 divided by fy. If you do the math, you will get 0.0033, right? You will choose the higher of these two. So, and row minimum, row maximum, we can calculate it by the equation that I showed you last time, times beta, which is 0.85, times 0.85 times fc prime 4000 divided by fy 60,000, and this will give you 0.181. And from here we can conclude that row maximum is here, which is greater than row, and row is greater than row minimum. Guess what? That means we are in the tension zone and the beam is ductile. Perfect. This is what we want. So let's now compute is the capacity and the demand. We have to compare the capacity and demand. So we know that demand, or phi mn, from the previous equation, or I can simplify the equation, is phi multiplied by as fy d minus a over 2, right? I have everything except a, so let's compute a. A is what? A as fy divided by 0.85 fc prime multiplied by b, which is equal to 3 times 60 divided by 0.85 times 4 times 15, and this will give me 3.53 inch. All right, so eventually phi mn equals to 0.9, which is phi multiplied by the area of steel multiplied by 60, 24.5 minus a over 2, right? This will give me, if you do the math, how much is it? 3683 inch K. We usually write the moment in feet K, so this is equivalent to 307 K foot. Now the moment that we have calculated was how much? Was 209 something, right? So phi mn equals to 307 K foot. Mu, which is the ultimate load moment that exists, the moment exerted by the ultimate load, is 294.8 K foot. Since phi mn is greater than mu, I'm safe. That's it. Okay, this is the end of this video. Hope you guys enjoyed. So now you guys can go and design any beam, simply supported, or even one continuous end, or both continuous end, or even cantilever. What will matter only is the way that you will calculate the moment, which is the ultimate load. Hope you guys enjoyed the video.